Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. Today we are going to continue with the Spark lecture. I'm going to hopefully finish it, and if time permits, I will move on to a few considerations for large scale and optimizations. What we did last time was the logical part of Spark. I wanted to mention, because there was a request at the end to give concrete examples. So if you now re-download the slides, you will see, I need to select the right window here to be able to click. If you go on the slides, you see at the bottom of the slides, then you have examples now of codes. Very simple, right? That was accelerated with AI, but this is what they look like when you actually apply them in PySpark in that case. All right. Who is comfortable with the logical model of Spark? Okay. Who understands the differences with MapReduce? Right, 3 of them. Instead of just two-phase, it's a full DAG, right? Directly the cyclic graph. Difference number 2 is instead of everything being a key-value pairs, now we can have collections of anything. It could be key-value pairs, but it can also be just values. And the third difference is that instead of just map and reduce, we have a whole collection of around 30 plus transformations and 20 plus actions that you can pick from. So all in all, what we can say is that it is more generic than MapReduce, and thus we call it the next generation of MapReduce. Now I'm going to go to the physical level, and as you will see, and I insist it's the next generation of MapReduce, so there should be actually no big surprise on the physical level because it will feel similar to MapReduce in spirit, with a few, of course, improvements that leads to the processing of DAGs, right? So let's go to the physical layer. So I'm going to start with the easy case. Who remembers from last week that some of the transformations felt spaghetti-y and some others did not feel spaghetti-y? Right? So the filter, the map, the flat map were not too much spaghetti-y, right? It was just every value is mapped to something else, just like here on the screen. And some others felt spaghetti-y, and I think of distinct, of sort by key, of intersection, like basically where the values are sent all over the place, and probably you start feeling there's shuffling going on here. So I'm going to look at transformations that are not spaghetti-y, and that look a little bit like this. We in fact have a name for that. This is called a narrow dependency. The idea is that each one of the values or key values that we have in the output here. Do I have my volume? Yeah, I thought for a moment that I was on mute because there was a pop-up on the screen. I am not on mute. I think people would have complaints. So we have the keys right here. And the reason it's narrow dependency is that every value here only depends on a few of the input. In that case, just one, could be a few more. But basically, it's narrow. It's not like you need everything in here to compute a value like this. Who is with me? Right? Okay, so as you can imagine, we are going to parallelize this in the way similar that we were parallelizing the mapping phase and the reduce phase of MapReduce. So I put these dashed lines in here. Surprise, surprise, we have tasks, just like the map tasks and the reduce tasks. Now we just have tasks for anything, pretty much. And what we've done is not very surprising. We've just partitioned the inputs, and we are computing the output partition by partition. Who is with me? Right? That's not surprising. That's exactly the same way we did it in MapReduce. That is the power of parallelism and batch processing. Why am I saying batch processing? Because we do not do them one by one. We have this batch, this batch, this batch, this batch, right? So every task gives you one batch. So we parallel and batch processing. Now, something also that shouldn't surprise you is that when we read from HDFS, we also try to have one task per HDFS block, right? Exactly like in MapReduce, where we had one split for every HDFS block. It's just roughly like that because you remember it's not an exact fit because the last record might actually spill over the next block. So it might be you still have a few more bits to read from the next block. But all in all, we try to have one per HDFS block. Who is with me? right? Of course, that only applies to the very first transformations that you apply when you read, right? If you're further down in the DAG and you're actually processing intermediate data, then you're far away from a GFS at that point, and that doesn't make any sense anymore, right? But the very first transformations that are applied right upon reading from a GFS, then you try to map the tasks to the blocks. So you have in mind the batches of 128 megabytes. So not surprisingly, again, we have the logical layer upon which we have an RDD that is mapped by a transformation to another RDD, that is the logical layer. And on the physical layer, we spread all of this on multiple machines where every machine gets one batch that we call task and executes the query. These would be the slots, right? So here I have 4 slots and 4 tasks, okay? But you might remember that every slot could process more than one task, right? Who remembers that, right? It's dynamic. We have more tasks than slots. And whenever a slot is done, they just take the next task, right? And when there's no more tasks, then they get idle. So basically, it means that the efficient slots, or the ones that were lucky and maybe got less to compute, will get more tasks because they were done a bit earlier. And the ones that are either very slow or were out of luck and just got a task that was much more complex to compute, they get less task, right? Who is with me? Right. But now I have a new name for you, executor. Executor. So an executor is the name that is given by Spark to the yarn containers. Do you remember the yarn containers? Right? These are the resources that we get when we want CPU cores and when we want memory from yarn, right? So we request the containers from yarn dynamically, and we call them executors. So what Spark is going to do is that it's going to request a lot of executors from yarn in order to do the computations, and it's going to spread over the tasks over the executors, right? Now, there's a little bit more precision that I'm going to give you, is that the executors might get multiple cores. Remember that when I told you a yarn container, it's a number of core and it's some memory, right? So they have memory, but they can have multiple cores. Now, do you remember that the tasks are one thread? Every task is a sequential invocation in MapReduce of the map function, of the reduce function, but it's sequential within each task, right? Who sees that because we have multiple cores in the executors, it would be inefficient? Let's say we have an executor that has 3 cores. Do you see it would be inefficient to just have one task at a time, right? You want one task per core. So slightly change here. For every executor and for every core of every executor, we have a slot, right? So the number of slots in Spark is the number of cores, right? So one executor might be executing multiple slots in parallel and might be evaluating multiple tasks, right? The memory is shared. I will explain a little bit, but basically the shared memory just gives a bit of flexibility, right? If you had the memory allocated for every slot, you might have inefficiencies because you might have one slot that is barely using much memory and another slot that is using a lot of memory. And so by dropping the barrier a little bit between some of the slots, it might be that this one uses a bit less memory, this one uses a bit more memory, and we just let the memory be shared in this way. It doesn't mean that they communicate. They do not communicate over memory. It's just that it's a bit flexible, right? Who is with me? Right? Very good. So the notion of slot is still here. The notion of task is still here. The notion of parallelism batch processing is still here. Here we are just learning that we have the yarn containers and every core gives us one slot which sequentially takes care of tasks. So now I just considered one transformation, right? It could have been filter, it could have been map, it could have been flat map, and we can execute this transformation like this, parallel, batch processed over the cores of the executors. The next step I would like to share now, and this is new because that we didn't have in MapReduce, is that we can have multiple transformations, right? In MapReduce, that didn't exist. We just had map, we just had reduce with the shuffle in the middle, but we were not chaining transformations in the way we do it in Spark, right? So I'm going to take an example with, in that case, 3 transformations, 4 RDDs, right? And I just have 3 transformations on my RDD. Furthermore, I'm going to take narrow dependency transformations, right? I'm not spaghetti transformations, just 3 narrow dependency transformations. Maybe the first one would be a filter, the second one would be a map, and the third one would be, I don't know, a sample, right? So basically just narrow dependency, non-spaghetti transformations. So we could get something like this, right? Where I just have machines that execute the tasks of the first transformation. Of course, maybe you can have multiple tasks for every slot. Then you basically maybe send some data around. Then you have, again, either the same machines or other machines that execute the task by task, the second transformation. And then machines that execute task by task, the third transformation. Who has the intuition that this is very bad and inefficient design? All right? This is what I would like you to see. This is inefficient. This is not the way that we are going to do it. But who maybe has an idea on what is inefficient in here that could be improved? I see raised hands over there. Maybe we can bring the microphones. You can also paste your IDs on Zoom, by the way. We see you.
Where's the hand?
Oh, there's plenty of hands. You can choose whoever you want to give it to. Yeah.
So I think it's probably these dependencies in the shuffle phase.
Yes, so here you mean, right?
Yes.
For example, yes, so maybe we could avoid changing it and maybe keep the same isolation, right? This is what you mean. That's a great idea. Another one, because there's so many things that are inefficient in here, you wouldn't believe. So maybe there's even other ideas on things we can improve. Maybe I see other raised hands.
I'm closer.
Yeah.
Thanks. I think we want to minimize the amount of network traffic. So we want to try as hard as possible to keep processing on the machine where the data from the last step was processed as well.
Yes. So in short, what you are suggesting is that here we shouldn't ship it to another machine.
Yes.
We should continue to do it on the same machine, right? Mm-hmm. Okay, yet another thing that kind of follows on what you said. This one is more subtle. That I don't know if you will actually get it. Over there, we have a raised hands too. Over there. I see a raised hand there. That's always short hops with the microphone because otherwise it can surprise people. It's over there. Yeah, go ahead.
The later machines are likely idle when the first machines are just starting.
So the machines, they are idle when?
When the whole process starts, the machines at the end are not doing anything.
Ah, yes. So you're saying that the machines right here, when the process starts, are not doing anything. You're absolutely correct. That is also a problem. In fact, it's a problem we even had in MapReduce version 1. Do you agree that this problem, which is a problem, is addressed by not changing the machine and keeping the same machine, basically? So this is also a problem, and we just address it by keeping the data on the same machine. So we don't send over the network, right? But that is also correct. That is an inefficiency. I see plenty more raised hands over there. Maybe we can, in small hops, very small hops. Exactly, perfect. Yes, awesome.
Maybe that one computer has many tasks and others in the same time have only one task on the right.
So here you're talking about the distribution of workloads, right? So you're also correct that this is something that can be inefficient. The way we solve it is basically by having multiple tasks per slot, because then when there is more workloads, there's going to be less tasks, and when there's less workload, there's going to be more tasks, right? So these are all correct answers. It's just that they are solved in a way bundled with other problems. But these are all correct answers, right? Anything else? Also over there, we'll go there also. Yes?
It seems that some machines will be done before others. There could be some stragglers. which will determine the overall
The
runtime.
stragglers, yes, we'll come to the stragglers in the next lecture. That is also a very good point. The stragglers are very important. This is very subtle because it's the sort of things that happens when you have a lot of machines. And it turns out you cannot solve that with software. You cannot do that with better code. I'll have a few slides extra for that. That's also correct. The stragglers are a problem. Yeah, I saw more recent, so let's try to go over there. Small hops. Small hops, yeah. We don't want to scare anybody with otherwise people are going to have nightmares at night with the microphones.
Yeah, I was thinking about stragglers itself. Can we like solve it with some sort of pipelining on the batches? Like not all the tasks are like doing in the same phase. Now we do not have to like wait for like a particular phase to finish before starting the new phase. We can just offload it like a bunch of the batches to the next task where the stragglers do the.
Yes. Yes, I think in spirit, that's exactly the last one that I was waiting for. You're basically 70 or 80% of the way on that, the idea of pipelining. So basically, if I correctly interpret what you said, you're basically saying that you should start here and go all the way here, right? In a pipelining fashion, right? Is it what you meant?
Not
No?
exactly. I was hinting on that, like before finishing, like while we are in the blue phase.
Mm-hmm.
So for all the machines, it might be that for certain tasks, the blue phase is taking a lot more to finish. So we can like, for the batches for which the blue phase has finished, we can already move to the red phase, whereas the blue phase is being executed. And then for like, if there are some stragglers in the red phase also, then we can, the finished jobs, we can move into the green phase. And we can have like some machines which do this hopping like at every cycle.
Yes, exactly. So basically you're saying we might compute the blue phase and some are done. And while some of the blue evaluations are still done, we already move on with orange and green. That is absolutely correct. Now we'll explain the 100% of the way. This was even 90% of the way, what you say. It's exactly the idea that since we anyway are going to run that on the same machines, we are not going to change machines, it's going to be the same machines. There is absolutely zero reason for synchronizing the steps. There is zero reason mathematically, because if you look at what's going on mathematically, in that case, it's so narrow that there's even only one row here. The purple is basically 3 function calls away from the blue one, right? And do you see that we can just directly compute the purple value on its own, just invoking the 3 functions on the blue one, independently of the others? So it means that this machine might go ahead and all the way to the purple, while this one is still all the way to the orange, and this one is on the green. They don't need to wait for each other, right? Who agrees with this? Right? This is absolutely correct. In fact, I can even tell you what's going to happen. So first, this is how we solve it. We stay on the same machine. In fact, what's going to happen, because within one task, remember, it's sequential. It's parallel across tasks, but it's sequential within each task and within each slot. So what's going to happen, to go further on your idea, is this one is iterating over the values. It takes the blue one, invokes the function, invokes the function, invokes the function, gets the purple one. Then moves on to the next one, invokes, 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 gets the purple one, right? Then goes to the next one, invokes, 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 gets the purple one. So it's basically moving. It's like a for loop locally that just moves through the values and invokes the functions all the way to purple. Who is with me? Right? Now, I would like to use a word I used last week to formally express what you've just figured out essentially. And you can tell me if you understand. We never materialize the orange RDD or the green RDD. At no point in time do we have at the same time this materialized in the cluster. The reason is that we just call functions directly from blue to purple sequentially, and we don't ever, once we are at the purple here, we throw away these intermediate results, right? So who agrees and understands the orange RDD and the green RDD are logically here, mathematically here, but they never get materialized on the cluster? Who understands this? Right? Very good. So it means that even on the local machine, if you consider this machine with that task, there will never be a list of these 3 or a list of these 3. right? You do have a list of these three because this is the input that it received. It's read from disk. You do have a list of these three because this is the outputs that needs to be sent further. You never have this list materialized. You never have this list materialized. They only exist mathematically. Right? Who is with me now? Right? Very good. So this notion of materialization is very important. So it means that machine by machine, we iterate on the input, and for every input, the chain of function calls generate the output. We only materialize the blue and the purple RDDs. I think we have a question on Zoom, but since Bojidar is getting the microphone, maybe I can take a look.
Yes, so why are you allowed to sequentially process the data from blue to purple? Don't you have some functions that need the whole data on the same level?
Mm-hmm. So you're basically questioning whether I can really iterate over the blue value and basically get the purple values as I go. This is because I assume that it's non-spaghetti-y. It's a narrow dependency. So I basically have this nice flow that is really highly vertical. That is the reason why I can do that, right? We'll take care of the shuffling a little bit later because the white dependency transformations like distinct, like group by key, like sort by key, that doesn't work, right? Who agrees with that? It only works with things like filter, like map, like flat map. Then we can do it nicely like this. Okay, so that's an excellent question, and I will come to the spaghetti-y transformations a bit later, where you cannot simply materialize purple by purple in this way. All right, so who is with me at that point? Right, very good. So we have a name for that when you do this. It's called a stage. A stage means we have multiple narrow dependency, non-spaghetti-y transformations that we squeeze together to be executed at the same time, right? It's a huge optimization, same machines, and we don't even materialize the intermediate RDDs, only the first one and the last one. This is called a stage. A stage is in fact a phase. It's just that instead, you know, people never want to reuse the same words. So instead of saying phase, they say stage, right? But a stage is basically the same as a phase in MapReduce. Okay, so that's new in Spark. We can squeeze together multiple narrow dependency transformations in this way that we don't need any shuffling or even any network communication on the server, right? So we have a stage that squeezes narrow dependency transformations. So this, again, is called narrow dependency. There is this assumption that there's locality in here, that we have the values that nicely produce the output values in a way you can just iterate from the left to the right in this way with a very simple for loop that goes over them. So now if I update the slide that I had earlier, I still have my executors, the yarn containers. I still have several cores for every executor. Every core gives me a slot. Every slot takes tasks one after the other. But now you notice the tasks are slightly different because since I squeezed multiple transformations that were non-spaghetti together, now within the same task, I have a chain of local function calls like this, where I never materialize the orange values. They are just intermediate values that happen in memory on the way to computing the green one, but I only materialize the blue and the green RDDs, never the orange one, right? So it's just an updated slide where in that case, I have how many transformations in here? Who thinks 1? Who thinks 2? Who thinks 3? It's 2, so the majority was correct, right? So we have the first one that maps blue to orange and the second transformation, orange to green. They are both narrow dependency. We squeeze them together in a single stage, and then the whole stage gets partitioned into tasks, right? So now we have squeezed together the transformations. Now, since we have this updated setup, it turns out that I can control as the user how many executors I want, how much memory I want in every executor, and how many cores I need in every executor by the magic of the command line interface. So when I have an application or a job I need to submit to Spark, there's the Spark submit command line, and I have these parameters, num executors 42, so it means I'm requesting 42 containers, 42 executors. I'm asking for 2 cores for each executor. How many slots do I have in total then? 84, yes, correct. 2 times 42. I have 84 slots that run in parallel. And then an executor memory is 3 gigabytes. So how much memory do I have in total? 126, correct. Because the memory is per executor, and 2 by 2, the cores share these 3 gigabytes. So every time you have 3 gigabytes shared by 2 cores with a bit of flexibility between the two. So you can modify that. I'll tell you a bit more how to optimize, but this is things you can optimize. You should, as a rule of thumb, always try to have less slots than partitions. So if you know how many HDFS blocks you have in your input, you should have a bit less slots than that in order to spread it a little bit over the slots, right? To avoid the idle machines, basically. Okay? And now I'm coming to your question on Zoom. What happens if we have spaghetti? What happens if we have a more complicated transformation like group by key, sort by key that basically shuffles everything, and then you cannot just map simply every input to every output value? Now it's more complex. So whatever is in here requires shuffling. Who has the intuition that group by key, sort by key, distinct requires some shuffling over the network? Right, very good. So think about it. Otherwise, it's really an intuition that you need to get. Whenever you have wide dependencies like that, you can't avoid the shuffling. There is no magic, right? You can't avoid the shuffling. It's like the taxes. You can't avoid the taxes. You also can't avoid the shuffling in complex data sets. All right, complex queries. So what we get is a stage, then we shuffle, then a stage, then we shuffle, then a stage, then we shuffle. And whenever we have multiple contiguous narrow dependency transformations, we just squeeze them together in a single stage. But as soon as we have a transformation that shuffles, then we need to change the stage and shuffle over the network cables. Who is still with me? Right? So you see, it's a generalization of MapReduce because we could shuffle plenty of times within the same Spark job. In MapReduce, we just shuffled once. In Spark, we shuffle multiple times. It's a big deal because remember that in MapReduce, when we needed to shuffle multiple times, then we needed to have multiple Spark reduce jobs that we changed together, remember, with the sequence files. So we needed multiple jobs for the complex queries, not in Spark, because in Spark, we can have general DAGs. And so in the same job, we can just shuffle 2, 3 times, 5 times, 10 times, right? It's just an arbitrary large job, okay? And of course, you remember that some of the transformations take multiple RDDs, so you might even have more complex things like this, where maybe in stage 3, you have the input joined from stage 1 and 2, right? So here you have the spaghetti within the spaghetti. You basically need to shuffle from multiple places, right? So you can imagine how heavy this goes on the network cables, right? When we have to do this, okay? But still, we have these stages, and the stages execute sequentially. Stage 1, then stage 2, then stage 3, then stage 4, right? Who feels they would be able, if I give you a DAG of transformations by looking at where are the narrow dependencies, where are the wide dependencies, who could figure out how to squeeze them together and how to organize the stages from a DAG? Who already have the intuition for that? Very good. You should try as an exercise, right? So do some random DAGs that you generate and see what you can squeeze together and figure out how you can group the transformations into stages like this. So this is the high level. So now that's an Eselsbrücke that I have here in order to just have a visual, because that's very complex with all this terminology. So how do transformation stages, jobs, and tasks relate together? So take a snapshot of that in your head. Basically, the transformations can be vertically squeezed together into stages when there's no spaghetti. So when there's plenty of narrow dependency, you can squeeze them together in a stage, right? And the stages get split into tasks. So basically, the optimization is that it's not the transformations that we split into tasks, it's the stages, right? This is the optimization we have, which allows us not to have to materialize the intermediate RDDs, right? So who understands this optimization that we have the task as a stage level? Yeah, see some raise hands? Very good. And then multiple stages give you a job. So this is how to remember this. Again, This is logical, this is logical, this is logical, this is physical, right? This is the physical implementation of the job and of the stages. Any questions so far? Who is with me? Not scared yet? Okay. Who sees all the stuff we've learned in MapReduce that also applies here? Right? There's a lot of reused ideas from MapReduce, right? So there's a few new ideas, but a lot of it is very similar to MapReduce. The way we have the tasks that execute on the slots, that is exactly the same idea. Now, just two things for tuning performance that are good to know. Here's a scenario where I have a DAG, and you know that it's lazily evaluated. So if I just have transformations, nothing is going to happen. But maybe then I have an action in here. So somebody invokes an action like collect or count or something. So I pull the string in there, and then it triggers the computation. Then somebody else pulls the string in here because that's stored as an RDD. So now you trigger an action here. It again computes everything in here. Then somebody calls an action right here, yet another one. And then that again triggers computations on the cluster. Who sees that this is inefficient? Why is that inefficient? We have raised hands over there.
Where's the hand again?
We should train an AI on seeing raised hands.
I think because it just does the same calculation 3 times until the bottleneck, so you can probably just cache it.
That is correct. Exactly. Both the problem and the solution that you correctly identified. So the problem is we compute that 3 times, exactly the same thing. That's exactly the same data. And you suggest to cache it. So indeed, we can cache it. I put this little thing in here. It's like we pin this RDD. And then when I call the action, we can keep only these intermediate results here, 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 and here. So you have the ability in Spark to explicitly cache the intermediate RDDs. You even have flexibility. You can say, please cache it in memory, please cache it on disk, please serialize everything even to just bytes, or keep it in memory with the full-fledged pointers and memory structure. So you have plenty of ways of basically indicating how you would like to cache your RDDs. But this is correct. We want to avoid recomputing the same things all over again. So it's quite common as a user to require Spark to cache. Of course, it's best effort. Sometimes Spark has so many things to cache and not enough memory or not enough disk, and then it makes calls. There's priorities, so this has higher priority, it will keep it. But you know, it's no big deal. What's the worst that can happen if we lose some data? We just recompute it. That's why it's called resilient distributed data set. So the worst that can happen is we just compute it again, right? Who is with me? Right? Very good. So that's optimization number 1. Optimization number 2.
There's a question on Zoom.
Oh, yes?
Whether on the previous slide, I think, the arrows represent the stages.
Oh, no, here, this was just transformations. I just had transformations in mind on the logical level, like do I persist the RDDs? It could have been stages, in fact. You could also consider that. But the idea is that the nodes in that graph are the RDDs, right? The nodes are the RDDs in here. Every rectangle is an RDD. And then the arrow express transformations. So if you really want a precise answer, these are transformations, and these are RDDs. And you would have to figure out the stages separately, but you can consider that it's orthogonal to the idea of stage. Does it make sense? Yes, but are the RDDs not materialized? No, generally you materialize them, but you might forget about them. What happens is that, imagine you have an RDD here, then of course you materialize the output at some point, you ship it over the cluster to this, and then they compute things, they materialize again, so you get the materialized 3 RDDs that are shipped over here. But what's going to happen in this case, if I don't optimize, what's going to happen is that once you have your RDD here, you can consider that this can be thrown away. So even though you materialize them, you might throw them away when they are no longer needed, right? So this is not the same as materialization. You do materialize them, but then you throw them away. The cache says, do not only materialize, also cache them. You materialize and you keep it. You pin it to keep it on the machine on a longer term than just for the duration of the computation of one transformation. Does it make sense? Yep, awesome, you're welcome. Very good, okay. So caching allows us to request that an already materialized RDD stays there for the longer term in case you need to reuse it for more transformations later on, right? So it's an improvement. Second improvement. The second improvement is called pre-partitioning. Let me try to find a way to explain this. Imagine, let's do it with a group by first. I can also explain it with a sort by, the order by. Let's do it with a group by. Imagine that I have an RDD, the blue RDD right here, and I have a group by. It could be, let's say, cities and inhabitants, right? And they have a canton, and I want to group by canton, right? So what I need to do is to compute the group. So here it's going to be city, 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 and here it's by canton. Every canton needs to obtain the data from all the cities within the canton, right? It could be from anywhere, and this is why we have the shuffling. So normally, in the normal case, it wouldn't be like this. It would be shuffling really all over the place, right? All over the place. However, in that case, the way I drew my slide, imagine that you know that all the cities of the canton of Zurich turn out to be in that task in here, Aargau also, Bern also, all those of Solothurn, Fribourg, Genf, they're all in here. All those of Appenzell, Tessin, and so on, they're all on the same machine. Do you agree then that we don't need to communicate across machines if my groups are already compatible with the machines? If each group is on only one machine. Who understands that? Right? So what I'm saying here is that if you have a wide dependency, I'm finding the slide here. This one here, a wide dependency transformation that could be much wider, right? You can have like 10 or 20 such squares, like full shuffle. If Spark has extra information, extra intelligence, extra information that it so happens that the data, the groups are already sitting on the right machines, then you don't need to send any data across machines. You can directly do that. Right? Let me now explain it with sorting. Imagine that we want to sort things. Let's say you want to sort numbers that are between 1 and 30. And you have intelligence, you have information that tells you it so turns out that all the values between 1 and 10 are on that machine, in any order, but between 1 and 10, they're here. The values between 11 and 20, they're in here. And the values between 21 and 30, they are in here. Who agrees that you only need to do local sorting, but you don't need to ship data across machines? Who sees that? Right? So this is what we call pre-partitioning. It's like the data is pre-partitions in such a way that you don't need to actually ship data across machines. So you have here mini spaghettis in each task, on each machine, but not across machines. So that means that when you have this information, for example, in here, it might be that here, let's say you grouped the data by a certain key, and it so happens that the join here is on the same key. So the group by key is the same as the join key. Do you agree that then, since we already grouped by key, they're already on the same machines? So do you agree we don't need to shuffle here, only there? Who understands that? Right? Or imagine that we sorted the data, and then we group the data. Then we don't need to shuffle twice, we just shuffle once, right? Who sees that? So continue to think about it offline, but this is the idea. In certain cases where we have a chain of normally shuffling transformations, but it turns out that the keys they're using are the same or are similar, then we don't need to shuffle every time. We only need to shuffle when it's needed. But in some cases, we can avoid the shuffling altogether if the data turns out to be pre-partitioned. And Spark is smart enough to figure it out, that to detect the cases where there's no need to shuffle across machines. You only need to do some local spaghetti. So that basically would mean that you have some local code that might be more complex than a for loop, right? But it's local to one machine. It's local to one CPU, so that's all local, not using any network cables. Okay, so this is what you can do in that case. Who is with me? Right? Okay, I don't see as many raised hands as before on that. So any questions on this? Who is unsure about understanding the pre-partitioning? Please raise your hand if you're unsure. I see. Are you raising your hands?
There's a question over there.
Oh, it's a question. Okay, so let me address the question. Yeah.
So does like Spark, whenever it has a new data set, it always performs a sort of pre-processing or scanning over like the complete table if we are inputting a table? Because like all these extra bits and pieces of information, they require like a complete knowledge of the whole data set that we are operating on. So like how generally is that?
So first, there are indeed cases where Spark is scanning an entire data set. An example of that is schema inference. Imagine you have a huge JSON lines data set and Spark has to infer the schema. In that case, Spark does indeed need to scan through the file and infer the schema. There are also cases where Spark needs to do some extra things while computing the DAG. For example, it turns out that when you want to sort data, when you want to sort an RDD into another RDD, Spark actually does need to do some computations to figure out what the sorting keys look like in order to prepare the partitions, right? So there are cases in which Spark needs to actually, it cannot be completely lazy. It does need to pre-compute a few things to aggregate. Now, when I'm saying that the data is pre-partitions, typically, it's not going to be pre-partitioned because you've just read it from disk, right? Because typically, when you read it from disk, it could be in any order. But it could be pre-partitioned in the sense that you've just gotten your RDD from another transformation. And if you've just received an RDD from a grouping transformation, then you already know the groups are on the same machines because of the way you've just executing it. And then if the next transformation uses exactly the same keys, the same grouping keys, the same join keys, the same sorting keys, then you don't need to shuffle again, right? You need to think about it. It's not always true, right? For example, if you just group and you need to sort, you might need to shuffle again. But if you sort and then you group, then probably you don't, right? You just need to play out the data flow in your brain. Does it make sense?
Yeah.
Right? Very good. And it's very common to do that, right? In SQL, who has already written in SQL a group by some key and also order by some key in the same query? It's quite common to do that. Do you agree that if I have a group by followed by an order by on the same key, I don't need to shuffle twice? I can just do it once. That's enough, right? That's exactly the idea that I want to convey here, right? Right? Any other questions? No raised hands on Zoom? We have 2 minutes until the break. So the data frames I'm going to do after the break anyway. So now is the time if you want to use one more question. Otherwise, you get a longer break, 1 more minute. Seems that there are no more questions. All right, and of course, don't hesitate to drop an email or ask on the forum if anything is not clear. We are here to explain to you, right? So thank you very much and see you in 15 minutes after the break with the data frames.